Hello guys, I'm Jefferson Berlin, a BSc student of the Mariano Marcos Memorial State University, Midlothian campus. Today I will be discussing about discussing and reporting about advanced photometry. What is photometry? Photometry is the quantitative measurement of daylight, and photometry is photometry is the science of measurement of light in terms of perceived brightness of human eye. It is distinct from radiometry, which is the science of measurement of radiant energy. As I said earlier, photometry is science of measurement of light. So what is light? Light is a electromagnetic radiation. But we but what we see as visible light is only a tiny fraction of electromagnetic spectrum, extended from very low frequency radio waves through microwaves, infrared visible light and ultraviolet light, to X-ray and ultra-energetic gamma rays. Our eyes respond to visible light. Detecting the rest of the spectrum requires an arsenal of scientific instruments, ranging from radio receiver to scintillation counters. Radiometry. Radiometry is the science of measuring light in any portion of electromagnetic spectrum. In practice, the term usually limited to the measurement of infrared, visible, and ultraviolet light using optical instruments. There are two aspects in radiometry, theory and the practice. The practice involves the scientific instrument and materials used in measuring light and including radiation, thermocouples, bolometers, photodiodes, photosensitive dyes and emulsions, vacuum phototube, charge coupled devices, and plethora of others. And we are interested in, however, in these theories. Geometric theory is usually simple topic that most texts on physics and optics discuss in a few paragraphs. Unfortunately, there are rarely discussed the topic in enough details to be useful, short to convoluted mathematics and obtuse definition. Geometric theory is simply and easily understood. Under geometry, there is radiant energy. Light is radiant energy. Electromagnetic radiation, which can be considered both a wave and a particle, depending on how you measure it, transport energy through space. When light is absorbed by the physical object, its energy is converted into some other form. For example, a microwave oven heat a glass of water when its microwave radiation absorbed by the water molecules. The radiant energy of the microwave is converted into thermal energy. Similarly, visible light causes an electrical current to flow into a photographic light meter, when it the which the radiant energy is transferred to electrons as kinetic energy. Spectral radiant energy. A broadband source such as the sun emits electromagnetic radiation through most of electromagnetic spectrum from radio wave to gamma rays. However, most of the radiant energy is concentrated within visible portion of the spectrum. A single wavelength laser, on the other hand, is a monochromatic source. All of the radiant energy is emitted on one specific wavelength. Radiant flux or radiant power. Energy per unit time is power, which we measured in joules per second or watts. A laser beam, for example, has so many milliwatts or watts of radiant power. Light, light flows through space, and so radiant power is more commonly referred as to the time rate of flow of radiant energy or radiant flux. In terms of photographic light, meter measuring visible light, the instantaneous magnitude of electric current is directly proportional to the radiant flux. The total amount of current measured over a period of time is directly proportional to the radiant energy absorbed by the light meter during the time. This is how photographic flash meter works. It measures the total amount of radiant energy received from the camera flash. And radiant flux is measured in watts. Radiant flux density or irradiance and radiance existence. Radiant flux density is radiant flux per unit area at a point of surface, where the surface can be real or imaginary. There are two possible conditions that flux can be arriving at the surface, in which cause, in which case the radiant flux density refers to as irradiance, and flux can arrive from any direction above the surface indicates that the rays is irradiance. Flux can also be leaving the surface due to emission and or reflection. The radiant flux density is then reflected as a radiant existence. As well as with irradiance, the flow can live in any direction above the surface. The definition of radiant existence is the importance of real or imaginary surface cannot be overstated. It means that radiant flux density can be measured anywhere in three-dimensional space. This includes the surface of physical objects in the space between them, and inside the transparent media such as water and glass. Radiance. Radiance is best understood by first visualizing it. Imagine a ray of light arriving or leaving a point on a surface giving direction. Radiance direction. Radiance is simply the infinitesimal amount of flux contained in the ray. A more formal definition of radiance requires that we think of a ray being infinitesimally narrow, fold with its apex point on a real imaginary surface. This cone has a different solid angle that is measured in strigan. Radiant intensity. We can imagine the infinitesimally small point of source of light that emits the radiant flux in every direction. The amount of radiant flux emitted in that given direction can be represented by a ray of light contained in an element cone. This given that the division of radiant intensity. Radiant intensity is measured in watts per strigan. Photometry. Photometry is a science of measuring visible light in units that are weighted according to the sensitivity of the human eye. In a quantitative science based on statistical model of human visual response to light, that is our perception of light and under carefully controlled conditions. Photometry may refer to field, optical, and astronomy. The human visual system is a marvelous complex and high nonlinear detector of electromagnetic radiation, with wavelength ranging from 380 to 770 nanometers. We see the light of different wavelength can continue of color ranging through the visible spectrum. 650 nanometer is red, 540 nanometer is green, 450 nanometer is blue, and so on. The sensitivity of human eye to light varies with wavelength. A light source with radiance of 1 watt per meter squared stereo of green light, for example, appears much brighter than the same of the radiance of 1 watt per meter squared stereo of red or blue light. In photometry, we do not measure watt of radiant energy. Rather, we attempt to measure the subjective impression produced by stimulating human eye brain visual system with radiant energy. This task is complicated immensely by eye nonlinear response to light. It varies not only with wavelength but also the amount of radiant flux, whether the light constant or flickering, and spatial complexity of the scene being perceived, and adaptation of iris and retina. The psychological and sociological state of observer and the host of other variables. Nevertheless, the subjective impression of seeing can be quantitatively for normal viewing condition. In 1924, the Commission of International Declare the Eclairage or International Commission on Illumination or CIA asked over 100 observers to visually match the brightness and monographic light sources with the different wavelength under controlled condition. And as a statistical result, the so-called CIA photometric sh- curve shows that the phototopic luminance efficiency of human visual system as a function of wavelength. It provided weighting function that can be used to convert radiometric into photometric measurement. Photometric theories does not address how we perceive colors. The light being measured can be monochromatic or combination of continuum wavelength that the eye response determined to the CIE weighting function. This underlines the crucial point. The only difference between radiometric and photometric theories is the unit of measurements. With this, though firmly mind that we can quickly review the fundamental concepts of photometry. Luminous intensity. Luminous intensity. The foundation of photometry were laid in 1729 by Piers Borger and his Liesel of Decade. Borges discusses photometric principles in terms of convenient light source in his time, a wax candle. This became the basic of point source concept in photometric theory. Wax candles were used as national light source standards in 18th and 19th century. England, for example, uses spermaceti, a wax derived from the sperm whale oil. These were replaced in 1909 by the international standard based on group of carbon filament vacuum lamp, and again in 1948 by crucible contained liquid platinum that is freezing point. Today, the international standard in theoretical point source has luminous intensity of 1 candela. 1 candela emits monochromatic radiation with a frequency of 540 times 10 raised to 12 Hz, or approximately 555 nanometer, corresponding with the wavelength of maximum phototopic luminous efficiency that has radiant intensity of 1 over 683 watts per steradian. Luminous flux or luminous power. Luminous flux is photometrically weighted radiant flux. Its unit of measurement is in lumen, defined as 1 all over 683 watts of radiant power at a frequency of 540 times 10 raised to 12 Hz. As with luminous intensity, the luminous flux of light with other wavelength can be calculated using the CIA photometric curve. A point of source having a uniform isotropic luminous intensity of light candela in all directions emits emits 1 lumen of luminous flux per unit solid angle or steradian. Luminous energy. Luminous energy is a photometrically weighted radiant energy. Radiant energy that is measured in lumens per second. Luminous flux density. Luminous flux density is a photometrically weighted radiant flux. Luminance is the photometric equivalent of irradiance, where the luminous existence is the photometric equivalence of radiance existence. Luminance. Luminance is a photometrically weighted radiance. In terms of visual perception, we perceive luminance, and it is an approximately measured on how bright of a surface appears when we view from a given direction. Luminance used to be called photometric brightness. And this term is no longer used in illuminating engineering because the subjective sensation of visual brightness is influenced by other physical, psychological, and sociological factors. Luminance is measured in lumens per square steradian. Lambertian surface. A Lambertian surface is a surface that has constant radiance or luminance that is independent on viewing direction. In accordance with definition of radiance, the radiant or luminous flux may be emitted, transmitted, or reflected by the source. A Lambertian surface is also referred as an ideal diffuse emitter or reflector. In practice, there are no true Lamberian surface. Most matte surfaces approximate an ideal diffuse reflector, but they typically exhibit semi-specular reflection characteristic of oblique viewing angle. Nevertheless, the Lambertian surface concept is useful in computer graphics. Radiosity. What is radiosity? Eh, Radiosity does not define an even mention in the term radiosity. This is not unusual. There are many photometric radiometric terms whose use is no longer encountered. Illuminance, for example, is used to be called illumination. It was changed to illuminance to avoid confusion with the act of illuminating the state of being illuminated. When Moon wrote the scientific basic illumination engineering in 1936, the luminous existence was called luminosity. And curiously, there was no equivalent term for radiant existence. So he coined the term radiosity to describe the density of radiant flux leaving a surface. So radiosity is described by Moon the, by described by Moon. Radiosity is described by Moon by density of radiant flux leaving the surface. The illuminating engineering of committee ignored Moon's proposal. Luminosity was changed to luminous emittance, and later to luminous existence, with radiance existence following the consequent. And meanwhile, the thermal engineering community adopted radiosity. So it's very confusing. Fortunately, we only need to remember that radiosity is the radiant existence. Visual photometry. Visual photometry is photometry in which the eye used to make quantitative comparison between light stimuli. So, techniques in visual photometry. One is the qualitative method, two, the comparative method, and three, the physical method. First, the qualitative method. The intensity of In qualitative method, the intensity was related to the familiar values such as the brightness prevailing during various weather conditions. The report served simply to draw a familiar expression or to paint a mind picture. Comparative method, Bulger had observed that the human eye adapts to large range of ambient lighting and so intrinsically unsuitable for determining intensity. It can, however, be sensitive, temporal, or spatial difference in intensity. Bulger had recommended the brightness be evaluated direct comparison of an unknown intensity with some known reference. The method can be classified as either extreme detection, thresholding or matching, and each of these related methods needs a reference of standard and comparison. And the last is physical method. Unlike visual method, physical techniques related intensity to some other physical effect. These techniques were adequate to give a good estimate of brightness of light source or surface indeed. Indeed, the capability of visual photometry exceeded what was demanded of it. So, physical photometry. For accurate work, Alexander Trotter admonished no more than a dozen of measurement could be taken before resting the eye. An ill-defined range of acceptability seems to pertain in each these variables. Even the mental states of expectation of the observer were of important factor. So photometry is not the measurement of an internal or objective dimension or force, but a sensation. It is difficult to make a quantitative measurement of our sensation. Two pigs under a gate make more noise than one pig, while it is possible to measure the amplitude of vibration in air which produce sounds, and so is estimate those which correspond the faintest audible sound and show and those which cause roar or large organ. Physical photometry is photometry in which physical detectors are used to make measurements. The advantages of using physical photometry is the objectivity, the precision, speed, and automation. In objectivity, the traction observer independent measurement was important criterion for both scientists and engineers at, of, at the turn of the century. And precision, while carefully practitioner or visual photometry had been achieving measurement precisely 1% or better for decades. So, and speed, where the astronomer made do with slow, technical, difficult photographic methods. The engineers demand speed and ease for use, drawing an analogy of popular Kodak camera, in which a slogan since 1886 had been "You press the button, we do the rest." And last, the automation. Closely allied to desire of speed was wish for the automation of measure, measurement of lights, part of general trend toward automatic control in engineering and industry. Uh, in measuring lights, we considered what are the instruments that we use in measuring lights. We use photometers. Photometers. Photometers is an instrument that can be used to measure illuminance or irradiance. These meters are often applied in industry as photometer. Photometer is a coherent term for detecting instrument. Most photometer work by using are either photoresistor or photodiodes. This work showing the change of electrical properties when exposed to light, which is easily detected using a suitable electronic current. Application of photometry. One is the transit photometry, a method for finding Earth. Advantages of this is transit photometry is currently the most effective and sensitive method for detecting extrasolar planets, particularly from the observatory in space. Transit can also provide scientists with great deal of information about the planet that is not otherwise measurable. Third, when combined with radial velocity data, a transit can also provide a good estimate of planet mass. And finally, transit photometry searches can operate a massive scale. Ground-based searches such as TRES, Google Hat or WAPS, and space-based search such as Kepler track as many as 100,000 stars at a time, a sign of transiting planet. Given the scale of searches, it's likely that transit photometry will soon surpass all other methods in sheer numbers of planets detected. Second application is luminance meter, are used to number industries to test brightness of displays, instrument panels, night vision devices, lamp sources, and etc. Luminance of small characters of cockpit display and instrument panels tightly controlled by aerospace in the aerospace and automotive industries by computerized qualitative control testing with spot photometer. And the third application is imaging photometry. This used in fast, accurate uniformity testing of cockpit display and automotive dashboard. These are suitable for ISO, ergonomic testing of computer monitors since both photometric and projection system I, both photometric and spatial measurement have to be performed in application. Luminance of creator screen in uniformity of projection system, transmittance of filter and reflectance of paper, textile, and ceramics are other common photometrics application. And as my report is being and will end now. So thank you for watching and listening to my report about advanced photometrics.